Okay, let's get started. I'm Dick Moberg, your host for this webinar. I'm filling in for Craig Maddox. Glad to see all of you here. I see some old friends from Europe have joined. Really appreciate that. Dr. Van Putten is on. So it's been a while since I've done one of these webinars. And so this is my proof of life webinar that I am in fact still alive and very excited to be hosting today. So why do we do this? Well, understanding and treating brain injury is a very big problem. It's like the weather, it's like cancer, it's a big problem. And big problems need creativity and community. And we're trying to help with both of these, particularly the community side. So we're trying to bring people together. We're trying to produce assets and resources that can be used by the larger community to help in this effort. And this webinar series is one of those. So I hope you enjoy this, and I hope you'll look at the past webinars. There's quite a list of them. They're all on our website and all on AI analytics, trying to solve this problem from the analytics side of things. We also have an amazing resource of educational aids on neuromonitoring.com. This has been developed by Ethan Moyer and a bunch of other folks have collaborated. We have a Discord community. We have a waveform wiki, lots of other things. You can link to the Cambridge lectures on brain monitoring through this resource. If you have ideas for that, please let us know. But we're trying to open all this up to the general public. A more recent effort is a Neurocritical Care Fellowship education program that we are helping with. And we realize that when you do a neurocritical care fellowship, your exposure to multimodal monitoring and advanced analytics kind of depends on where you do the fellowship. So we're trying to fill in some of those gaps with some of the educational aids that we've developed. We're working with quite a few universities to figure out what should that education be for a neurocritical care fellow. So if you have any ideas for that, also please let us know. I want to call your attention to two events coming up in the fall. The first is the annual meeting of the Neurocritical Care Society in October in Seattle. We've decided to get a large booth at that meeting. It'll be half showing our products, our clinical platform, our analytics studio, our agentic AI solution called Clara, some ideas for non-invasive sensors. But another part of that booth will be a meeting area where we hope to have a technology showcase, and we're going to open that up to academia and academic and industry partners. If you have ideas and you want to show them, or if you have algorithms or models or a sensor, whatever, we invite you to connect with us, and we can give you a little space in our booth there. So again, we're trying to make this effort about community as well. Another event going on at Neurocritical Care Society is the second annual Informatics, Big Data, and AI workshop. We were one of the kind of founders of the first one last year. It was highly successful. It filled the capacity, and we were asked to do it again this year. So Ethan has done a great job of organizing that. The topics will be on things like metadata and harmonization, data formats, conversion, data cleaning, regulatory, algorithms such as cerebral autoregulation, and visualization and modeling. So if you're interested in that workshop, go to the Neurocritical Care website, and you have to register in advance for it. So with these webinars and with pretty much anything we do, our company is very involved in research, external research, and community efforts. Please give us feedback on things we could do and or things we're doing and we could do better. So thank you very much. So let's get on with the webinar. I think most of you are familiar with Zoom by now. So please put any questions in the Q&A tab that should be at the bottom of your screen or wherever that little bar ends up. And then we'll get to these at the end. So let me get on to our featured speaker. So today we're very happy to welcome Inayah Hodžić. to our webinar. She lives in one of my favorite cities in Europe, in Amsterdam. She's an AI researcher from the Department of Neurology at the Amsterdam University Medical Center. She earned a dual MSc in Biomedical Sciences and in Medical Informatics from the University of Amsterdam. Her research focuses on EEG-based machine learning models for neurological outcome prediction in patients with postanoxic coma. We've been involved in a number of other studies along those lines, and her talk is going to be very interesting for this. So most recently, she's been expanding her work toward the clinical implementation and valorization of AI-driven decision support, which is perfectly aligned with the goals of bridging the gap between machine learning research and real-world neurocritical care, which is what we're all about. We learned of her work while we were on a call with UMC because they were looking for ways to implement their algorithm for study and eventual clinical practice. And this is often how we learn about really cool work being done in what we do. And so we heard her talk, and we got to know her and invited her to do a webinar, and here she is. So I'm very happy to turn it over to you. So let me stop sharing, and you can share your screen.
Yes, I will. Let me see. Let me expand. I hope it is in presenter mode right now. If it's not, please let me know. So yeah, thank you so much for that introduction of how we met and the work that I do. So without further ado, I will take over. So as was introduced, I'm here today as a representative of a team of researchers, part of the neurology or the clinical neurophysiology department at the Amsterdam University Medical Center. And we are one of the largest clinical neurophysiology departments in the Netherlands. And besides clinical work, we also do a lot of clinical and translational research on neurological disorders, neurological states, and movement disorders, so tremor, epilepsy, and the one that I'm mostly involved in, which is postanoxic coma. And today I want to particularly highlight one of our more recent works, which was a poor neurological outcome prediction in postanoxic coma using deep learning, so what we termed a continuous convolutional neural network. And to get into it immediately, a little bit of context about postanoxic coma before we begin, for those who might not be completely familiar with it. So many patients are admitted to the intensive care unit each year with postanoxic coma brain injury after cardiac arrest. And about 80% of the people who are admitted in this way are actually in a comatose state, of which about 50% never regain consciousness again. So in the Netherlands, we're talking about 5,000 patients each year. In Europe, that increases to about 173,000. And in even larger populations like the US, we're getting close to about 500,000 people each year who suffer from or experience postanoxic coma. And the outcomes of this neurological condition they vary very widely. So it can vary from complete full recovery, neurological recovery, to persistent coma or even death in some cases. And as such, doing neurological outcome prediction, having some sort of expectation of the recovery trajectory of a patient is therefore very crucial for multiple reasons. Firstly, that it can support early communication with relatives and set realistic expectations regarding potential recovery. It can aid difficult treatment decisions, give a certain new perspective, or at least another multimodal factor to take into account. And lastly, perhaps one of the most crucial parts is that it can help prevent futile care. So if someone is very obviously in poor condition, providing them care is in this case futile, and can have negative effects. Or the complete opposite side, we can have unjust withdrawal of life-sustaining treatment, and if it ends up that that person could have recovered, that's a very catastrophic consequence that we want to avoid, which is why neurological outcome prediction is so crucial in this condition. And specifically, EEG is a very valuable indicator in prognostication, and it's also a key tool for prognostication of these patients. And particularly because distinct EEG patterns have been shown to correlate with different recovery outcomes. So a patient may be resuscitated after cardiac arrest, brought into the ICU, their EEG recordings might start, and then the different patterns can be visually seen within the EEG recordings. And a neurologist or clinical neurophysiologist has to weigh all these different patterns that might indicate one or the other and create an as accurate as possible outcome prediction for further treatment and the recovery. And I have a beautiful photo here that I've taken from Hofmeyr and Fulton. And this shows two very distinct continuous EEG recordings from two different patients. And we can see here in the beginning sort of a very low voltage isoelectric or nearly isoelectric activity in both cases. But in the top case here, we see an evolution of the EEG to a more continuous pattern, so within the 12 hours, which continues evolving to an even more continuous pattern at the 24-hour mark. And the 12-hour and 24-hour mark are very important key moments within when it comes to EEG recordings, and many guidelines actually encourage the outcome prediction to be either 24 hours or around this hour, with some indicators already appearing at 12 hours. But those are key moments within the entire EEG, continuous EEG in clinical practice. But in contrast, we see here on the bottom a different kind of EEG recording, which is, again, it starts isoelectric or nearly isoelectric, which continues to about 12 hours. And then we start seeing this peculiar pattern, which we call burst depression, where after there's again a kind of a return to the original isoelectric low voltage activity that we see here. And those who are familiar with EEG might therefore not be surprised that the top EEG recording here was from a patient who eventually ended up having a good outcome, and the recording at the bottom is from someone who ended up having poor outcome. So in this way, the EEG is visually inspected. Different EEG patterns are identified, and as such, a prediction is made. But many more different patterns exist, and they can all combine. So I have 4 other examples here that I show you, again, which is around these very important hours of 24 and 12. So you can imagine once the myriad of patterns increases and they start mixing and you have more ambiguous cases, the visual inspection and outcome prediction that results from that becomes more difficult to do and more ambiguous, and the cases become even more ambiguous at some point, which makes it complex for a neurologist or neurophysiologist to be able to do a correct and timely prediction. So visual inspection therefore has certain limitations. So there's just extensive expertise required, years of training, continuous exposure to such patients and EEG recordings, which is not always readily available in every hospital. And even so, it is reliable in about 50% of the cases, because it's such a complex and nuanced skill set and procedure that needs to be done. And I can imagine that if there's any doubt or ambiguity, you take the benefit of the doubt. And as such, it becomes reliable in around half of the patients. And besides that, it is simply time consuming if you have large chunks of EEG to look at or ambiguous cases, and these EEGs are subject to interrater variability between observers. And that has brought forth the question, not only to us, but research in general, what if we could automate EEG pattern analysis and outcome prediction to perhaps get an even more accurate and even more objective and a quicker outcome prediction or prognostication for these patients? And machine learning has recently emerged as a very valuable tool to help aid this. So we've seen that deep learning especially has been shown to consistently outperform other methods in EEG classification tasks. And the underlying reason partly is that they have this capacity to employ additional features, identify certain patterns, maybe spatial patterns or other types of patterns that are invisible to the naked eye, as well as take into account certain temporal dynamics of the EEG, which perhaps you can't see when you look at isolated windows of particular hours. And what we observe then in literature, that a lot of machine learning models are actually trained still on data from isolated time windows. So very common it was to see 12 or 24 hours, or in combination with 48 hours, which I think leads back to the original protocol, and that the 12 and the 24 hours are denoted as key time points within the EEG. But we believe that deep learning models, specifically such as CNNs, could, in addition to just looking at the isolated windows, capture certain trends and this dynamic evolution, what I showed you before, which is very important. The context in general is very important, and certain patterns might be interpreted a little differently depending on what came before or what came after. So that kind of evolution of the EEG signal is a very important part of prognostication. And in some cases in practice, such specialists don't even have time to look at the entire, scroll through an entire EEG signal, even if they want to. And as such, it often becomes restricted to these 12 and 24-hour periods. And as such, we believe that if we could employ deep learning models, we could perhaps come up with a method that could lead to more accurate predictions in general, that could enable prediction at any point during treatment. So instead of waiting for the 12 and 24-hour mark, it could give an indication of outcome at any point in time and maybe continuously update at certain points. And lastly, we can then use it to investigate further and see if there are moments when EEG is most predictive, or even if there are moments where it is a little less informative. And that could be a very important indicator for future work and indication, and how we look at the EEG signal in this context further. And what comes with that is that EEG data over long temporal windows, which we would need for this sort of approach, does have a practical limitation. And we found actually that, or in research, it has been suggested that a reduced number of electrodes, so instead of having the full set, or maybe like the 9 electrode set that we use at the Amsterdam UMC, that reduced number of electrodes results in comparable model performance when it comes to such EEG classification tasks. And the practical limitation that we're talking about is that it takes, once again, dedicated staff to be able to apply this. It takes time, it takes a certain expertise again, and dedication, which could be partly reduced or resolved by the employment of a reduced number of electrodes. So taking everything into account that I've said so far, the aim of this particular work was to develop a deep learning method, so a continuous convolutional neural network, which I'll explain more later, to predict poor neurological outcome in postanoxic coma patients from cardiac arrest, abbreviated to CA, to 72 hours after. And we also wanted to compare a 9 electrode model, so what we use standardly, to a reduced 4 electrode model to see if there are significant differences in performance and perhaps the predictive power as measured of the EEG by these different electrode configurations. So in order to do this, we performed a prospective cohort study with EEG from 366 postanoxic coma patients that were admitted to the Amsterdam UMC hospital between 2014 and 2022, I believe. So the EEG was started as early as possible and continued to record up to 72 hours after cardiac arrest. And between 2014 and 2019, so a span of 5 years, the EEG that was reported continuously was not yet used for clinical decision making, as it was not yet part of the protocol or guidelines. But as such, we believe that that was not subject to self-fulfilling prophecy, which I will come back later to. So our main outcome variable was neurological outcome, which we operationalized by choosing the best cerebral performance category score, CPC, within 6 months after CA. And the CPC score is a 5-point scale, which is an indication of the extent of neurological injury and functionality and disability as well, which is assessed clinically multiple times after cardiac arrest. So it can range from a CPC1, which indicates full recovery or mild disability, to CPC5, which indicates death. And in order to train a sort of binary classification algorithm, we had to dichotomize this as poor and good outcomes. So it's pretty standard in similar research to have CPC1 and CPC2 denoted as good outcome, and patients who had CPC3 or above were assessed or assigned poor outcome at discharge. To then move on to the pre-processing of our EEG signal. So we had, as I mentioned, EEG recording. So our first electrode configuration was a 9-electrode montage and recordings at each individual hour from TE0. So TE0 is or denotes the return of spontaneous circulation, that is T0, and T72 is 72 hours after cardiac arrest. So what we did is we had a custom-made algorithm to select the best 5 minutes or an epoch of the best 5 minutes of the EEG signal within that hour. So it looked at parts of the EEG signal that had the least artifacts, also that the total microvolt was below 200, I believe. And once this was selected, this was then stored in a database, and this was repeated for each hour and for each patient, so keeping track which EEGs belonged to which hour and which EEGs belonged to which patient. And then we also repeated this for our 4-electrode montage. So for our 4-electrode montage, we selected certain channels, as you can see here in gray, from the original 9-electrode recordings that we had. And once we had our pre-processed EEG data and stored in this particular database, we could start looking at our deep learning model. So I want to briefly talk about convolutional neural networks in general. So these are a particular type of deep learning models, and perhaps you may know, but just to reiterate, and they're very efficient at learning certain patterns, and specifically spatial patterns and features in image data, where they were originally made for and still used very often today. So the idea is that we have an input image and certain filters. So in this case, they're also called kernels, but in this case, it's a single filter in a very simplified diagram here. But the idea is that these different spatial features or kernels can slide over the original input image, and through a convolution operation, gain a particular feature map, which is obtained from the input image. So the convolution operation and exactly what kind of feature map you have depends on the type of kernel. So my example is an edge detection kernel, so you can detect the different edges of the image of this cat here. But usually convolutional neural networks have multiple of these convolutional operations stacked over each other, and this allows a buildup of certain complex features and recognition of complex features. So it may start with detecting contrasts and edges and corners, and eventually through multiple layers, build up to very complex features such as recognition of the eyes or the nose or the ears in this case. And then you also might have certain pooling operations like a mean and a max pooling operation in order to compress the feature maps that can become very large and computationally heavy. But the idea is that you can slide these particular kernels over the input image and obtain certain features from the original input image, which you can then use further, and the network can train further in order to learn a particular classification task. So, for example, learning that this is an image of a cat. But what's very interesting about this, we're talking about input images. So these are usually two-dimensional types of data. So you have the height of the image, you have the width of an image, over which you can have different kernels slide and perform this convolutional operation on. But that's the first problem that we had, is EEG data is fundamentally different from such images. So it's time series data. And if we, for example, zoom in on a particular part of this data here, we can apply the same principle. So have a convolutional filter slide over the signal right here and identify underlying features and patterns. But then we have the very big underlying elephant in the room, which is what about the rest of the channels? So we have here, and that's the thing with EEG data, we have a third dimension. So we don't just have the signal itself, so the height of the signal, let's say, we have the signal over time, but then we have also very distinct EEG channels, which all measure its own thing. So you can't really let this behave as a regular image, let's say. And that's the first problem that you really have to look at when you're dealing with EEG data and time series data, is that you have three different dimensions that you have to work with. So our first big task was, how are we going to apply the same principles or a regular CNN to such interesting and complex data? But luckily, research is very vast, and Schurmeister et al. Are researchers who have actually created an adaptation of the original convolutional neural network, specifically adapted to work for EEG data. So this is a figure that I took from their very brilliant paper, and the shallow version, so it doesn't have many layers. But the idea is that the first initial step, convolution step, is split into two distinct steps. So they call it a temporal convolution, in which we convolve over the time dimension, while then afterwards they introduced some sort of spatial filter, which slides over the data in the channel dimension. So usually what is maybe done in one step, they split very cleverly into two distinct operations. And this allows to, first of all, capture the integrity of the signal over time, and then also be able to see spatial relationships within the signals, but kept separately over all the possible electrodes and the electrode channels. And afterwards, we had a pretty standard mean pooling operation to compress the complex feature maps. And the final layer is a classification layer. So they had a classification of hand and feet and rest. But in this case, for us, that would be the classification of poor versus good outcome. So this was the base of our deep learning method, or continuous convolutional neural network. But then we have a second problem, which is that you can apply such a CNN and train it on data obtained from one singular hour. But how do we then combine or extrapolate to predict over multiple hours? Because each individual hour has its own characteristics and should be kept separate rather than training it over the entirety of the signal. And our idea for this particular problem was, as I've been leading up to, is the creation of a continuous convolutional neural network. So what we did is we had those 5-minute EEG epochs. We split them into an 80% training set and a 20% test set. And we trained 72 separate CNNs on each individual hour and data obtained from that hour. So we had a CNN for data of hour 1. So that included all EEG epochs that we had over all of our patients, but specifically of the first hour after cardiac arrest. Then we trained a separate one on hour number 2, hour number 3, hour number 4, all the way up to hour 72. And this allowed us to keep the separate hour and the characteristics which are typical of the different hours separate, while also creating a method which could integrate predictions at each hour. And that particularly worked like this. So once the training of all individual CNNs was done, we took patients from our test set. So just to clarify, if a patient was in the training set, they were not in the test set, and vice versa. So it was unseen data, and the hour, for example, of patient number, let's say patient I here, was tested on the specific CNN of hour 1, which yielded a prediction of outcome, so pro versus good, at this particular hour. Then for the same patient, all the data of hour number 2 was tested on the CNN, which was trained on this particular hour. This yielded a prediction of the same patient at hour number 2. And this continued for all data that the patient had. So if they had the full 72 hours, we have 72 different predictions. And then to combine all of those, we took the average of all the prediction of that particular patient over all hours into a final one. And this was considered the final overarching prediction of this particular patient, whereafter we could compare our encompassing prediction with the actual true outcome for that particular patient. And that is what we did for all the patients that we had in the test set, so about 20%. And once we did that, we employed a relatively standard 5-fold cross-validation operation. So we had performance metrics over all possibilities. We averaged that across the 5 folds. And then additionally, we repeated that about 25 times in a bootstrapping procedure, so 25 iterations, where again, we averaged over all performance metrics for every iteration. So in this way, we were able to create some sort of system that allowed to track how the prediction changed over time and have the most common prediction weigh more heavily in the final average point. So if we look at the individual data that we had at each individual data point, in this configuration, data included at each hour is independent of all other hours. So the CNN trained at hour number 1 contained only data of hour 1. The CNN at hour 2 contained only data at hour 2, etc., etc. And I also forgot to mention, but we repeated, so we trained 2 separate models, one for the 4-electrode configuration and one for the 9-electrode configuration. But back to this, we still have that same question from before, which is how can we capture then trends between different hours and capture an evolution within the signal if we're completely treating them as kind of isolated, independent pieces of data. So in order to investigate that further and see how can we alter our approach here in order to get a more all-encompassing view over how the EEG evolves over time, we created a second model. So we had 2, now we have 4 for each electrode configuration, and we call this the cumulative continuous CNN. And so what we did is, instead of having isolated data points or databases of each hour, data at each hour increased cumulatively, meaning that at hour 3, we not only have data from hour 3, but everything that came before. And as the hours increase, so the number of CNNs also increase, the total data which was included in the training process would increase. And in this way, we could keep track, hopefully, of how the EEG signal changes over time, and what this added value is of keep adding more and more data, and perhaps we thought that having more data could maybe alter or reveal new patterns that an independent approach like here could not. So we tested the 2 electrode configurations, and we also trained 2 separate models, so the independent model and the cumulative model here. So this is a graph of all the data, kind of the distribution of the data or the data availability over the different hours, split between good and poor outcome patients. So as I mentioned before, we had about 366 patients in total, of which 164 had eventual good outcome and 202 had poor outcome. And so we see that the earliest EEG recordings were around T is 5, but very little, although above 50 patients. And then we saw a consistent increase in the number of patients and also the data available per hour, reaching a peak at around T is 24, in which again there's a slow decline in the total data available. And very interestingly, after this 24 hours, we see that more patients with good outcome remain rather than poor outcome. And again, very late hours had about the same number of EEG recordings available at the very start. But this is a point that I'd like to get back to later, but this is just to give an indication of how much data we had and how it changed. So data availability changed over time. So to then get into the actual results of our models, so we have here an ROC curve of a 9 electrode model and the 4 electrode model, so pretty standard. And interestingly, if we look at the table below in our 3 performance metrics, which are the AUC, the area under the operating curve, the accuracy, and a metric which we termed or abbreviated as SE100. And this is a very important metric for us, which and it stands for the sensitivity at a specificity level of 100%. Or in other words, it's the sensitivity of the prediction at a false positive rate of 0. So this is particularly important because with this metric, we set a requirement that patients with good outcome are never wrongly identified as having poor outcome, how many of the remaining patients are then correctly classified and predicted as having poor outcome. And this is particularly important because in certain cases and neurocritical cases like this, having a false positive has much more catastrophic and negative consequences than having a false negative, for example. So if you predict someone who actually has good outcome as having poor outcome, is a scenario that you want to avoid at all costs. So here we said, if we set that requirement that someone with good outcome can never be classified as poor outcome, in that scenario, how well did our model perform? So that's this metric right here, and it's something that we continue to look at very often. So if I start with the accuracy level here, that we see that there's actually not much difference between first the cumulative model and the independent model, and also not between the 2 electrode configuration. However, when we look at the accuracy, we see that there is quite an increase, and I want to say a significant difference here in the accuracy between the cumulative model, so the model in which we cumulatively increased the data each hour, in comparison to our independent model where we kept the data independent and isolated at different time points. And again, if we look at this third metric, we also see quite a substantial difference, and that the cumulative model performed quite some bit better in comparison to the independent model. And this are metrics over the entirety of the signal. So this is the performance averaged over all the hours. But perhaps the more interesting question is, so how does the performance and perhaps the predictive power of EEG then change over time? And that is shown in the following figures. So this is, again, the cumulative continuous CNN for the 9-electrode model and the 4-electrode model. And we see that there is this interesting pattern that we observe. So there's an increase in performance around that 5 to 6 to 7 hour range, but starting from 8 and lasting to about hour 12, we see that there's a peak in performance, particularly in these hours, which also persists in the 4-electrode model. But the moment that we add data from TS18, we see that the performance substantially drops and then doesn't really recover at any point, which is very interesting to know that there's added value in adding data, but only to a certain extent. And if we look at the individual hours, this effect also seems to be present. So the peak is still around that 6 to 14 hour ratio, where after there's a drop in performance specifically for the SE100 and persisting over the 4-electrode model as well. So what does that mean? So first of all, just the main finding here and main implication is that EEG recorded during the earliest hours after CA seems to be highly predictive of neurological outcome, and that the fewer number of EEG electrode is equally sufficient. So the difference in performance is negligible between the 2-electrode configurations. And how can we actually explain this if we look at the kind of neurobiologic core of this? And in fact, it's actually a support of earlier hypotheses that we had or exist in research. So the idea that early prediction is very critical and that reduced electrodes do not compromise EEG prognostic accuracy, something that was hypothesized for a very long time and proven in context of visual inspection. And the idea is, or the suggestion is, that the EEG tends to evolve to less specific patterns over time, and that therefore that the earliest patterns are most distinctive and most indicative and informative of particular outcomes. And then postanoxic brain injury tends to be a generalized condition rather than localized. So even if you reduce the number of electrodes that you use to measure, you would still have those ubiquitous EEG patterns that persist because it's a generalized type of brain injury. But what does this then mean clinically? What are the clinical implications of this? So it suggests that the acquisition of early EEG may be critical for capturing the most informative window for prognostication, and therefore we hope that this encourages the early and timely measurement of EEG recordings. So early EEG recording is part of European guidelines and current protocols, and many hospitals have EEG set up and readily available within the 24-hour period. So we believe that it's important that we can further encourage the continuous early measurement of EEG, and that it could prompt closer monitoring, facilitate further communication, as I said before, and also set realistic expectations, as well as initiate early multidisciplinary discussion. So EEG or neurological outcome is never solely predicted or based on EEG. It's a very multimodal approach, but having some sort of indication or more accurate indication in earlier hours may prompt all these other facets or aspects of clinical care, which are very important. So we hope that maybe this could contribute to an eventual shift in clinical practice. So having early EEG setup, early visual inspection, and also the use of a reduced EEG configuration to aid more accurate and more timely EEG initiation and recording. So very quickly, I want to talk about some limitations. So we did not externally validate, so this is only an internal validation. Then there is always the risk of having self-fulfilling prophecy as a factor, although I said before, for 5 years, it was not used in clinical decision-making, and we believe that self-fulfilling prophecy was not applicable. But there were also a lot of external factors which could have led to, or at least had an influence on these results here. So as you can see, starting from the 40-hour mark and down, the number of poor outcome patients is significantly reduced in comparison to the good outcome patients. So you have patients with poor outcome who are perhaps already passed away in the meantime or been discharged, et cetera, which could explain this sudden urge or surge in performance scores, because you are left with a lot of patients who have good outcome. So there's a level of survivalship related selection effects here. And of course, the treatment decisions can also affect the EEG signal, the integrity of the signal, and kind of the overall effect in the EEG evolution and distribution of patients across time. So what could be next? So we think that continued research and implementation of machine learning holds substantial promise for improving prognostication. So we believe further research could do or elucidate other nuanced temporal dependencies, and also look at even more serial dependencies between EEG epochs. So for example, long short-term memory networks are another type of deep learning model, which take earlier predictions into account when making current predictions. And introducing such influences and temporal dependencies could even further improve and elucidate the performance of the model, as well as the predictive power of EEG. But to end here, if there's anything you remember from my talk here, is that we have shown, or hope to have shown, that early EEG measurements for poor neurological outcome prediction is highly predictive, that reduced electrode configuration is an equally sufficient alternative, and that combining these findings may lay the foundations for implementing machine learning during EEG assessment and lead to better, timely, and more accurate predictions. So I will conclude. I have talked a lot, and if you have any questions, please let me know.
Well, thank you so much. It was an excellent talk. And we'll wait a little bit to see if questions come in. Well, we do have one here. So can you see the questions, or do you want me to read them?
Yes, I see a question. I'll start with the top one. So maybe I could just read it.
Yeah, sure.
Justin Morris says, or asks, I'm curious about the choice to use raw EEG input as it would appear on a display for the CNN rather than a frequency domain representation. Was frequency analysis considered, and if so, what motivated sticking with the time domain approach? So as far as I remember, we didn't look very much at the frequency domain representation. I thought it was important to let the model learn any spatial features or any spatial representations from the raw EEG input as much as possible. So I didn't want to add a lot of sort of pre-processing steps further, but to see, can it just, based on the raw EEG input or output that we get from a recording, could it just individually find spatial relationships that maybe we haven't even thought of? So it was kind of a choice to see if the integrity of the raw EEG signal was good enough to lead to accurate predictions. And but that's certainly something that can be further researched and would be very interesting to do if any other representations of the EEG signal could lead to even better performance. Yeah, so I hope that answered it to an extent.
No, I would actually just comment on that. I think that if you look at things like burst suppression, they're probably, that pet is probably best picked up in the time domain. And if that was kind of what it was,
right.
I can see that. I can also see what Justin's talking about in more of the background activity.
Right.
Frequency domain may be better for that kind of stuff, but cool, nice.
Right, and then we have a second question from Louise. Great talk. Sorry if I missed this part. It was not clear to me whether you used only the best 5-minute epoch within each hour, or if you used all of the epochs. So good question. And we did only use a single 5-minute epoch, so the best one. So each hour for each patient would have only one single epoch. But we also considered, and which I also suggested as future research in the publication, is that perhaps 5 minutes epochs are, I think, standardly used, are very commonly used, but perhaps it would also be valuable to increase the time period here that we use. So not just 5 minutes, maybe 10 minutes or 15 minutes, and see if that could also improve or lead to any change when it comes to the performance of the model. But for now, we used indeed only one.
Well, I have a question while we're waiting for some more to come in. As somebody from industry, I'm always interested in how do you translate these kinds of things into clinical practice? So,
Right.
in terms of like what are the barriers? And so two questions come to mind. In your particular institution, like post cardiac arrest, do they currently monitor EEG? I mean, is it something that's immediately done? And then the second part of the question is really the whole, withdrawal of life support, and you touched on that. In trying to avoid a nihilistic approach, from the beginning. So I guess, do you already monitor EEG, and then how would you address the withdrawal of life support?
Yeah. So to answer your first question, so at our medical center, continuous EEG is used as standard practice. We have a large center with a lot of capacity, which is obviously part of it. But EEG is started as early as possible, and I think most are started within the 12-hour and perhaps even within 6 hours of arrival. Yes, so we do that. We do continuous EEG and continuous monitoring, and as long as possible, because we have the capacity for it. But we also know from many other hospitals that that's not always possible. So we're very in a unique position when it comes to that part. And if you could repeat your second question, now I've distracted myself.
When you're doing any kind of, I guess, prognostic score,
Mm-hmm.
and you want to use, the question is, if your algorithm determines they're not going to do well, does that just trigger as you said, is a self-fulfilling prophecy? I mean, you said that on one of your slides. So how, and that's come up as a question. I think Netherlands is very different from the U.S. in terms of attitudes, and you see that as a kind of country to country difference. But what do you do? I mean, how do you address that? I'm sure you've thought of it.
Yeah. So that's an interesting point. So I do want to reiterate that that right now in the guidelines and the protocols, treatment decisions based on this prognosis are not done before the 12-hour and the 24-hour mark. So even if I were to implement this on, let's say, on the ICU right now, it would be very difficult to have a very quick action taken from an algorithm that maybe predicts poor outcome at, let's say, hour number 3, which is why also I think it's important that I mentioned that perhaps for now, that's also not the goal. The idea is to get a better picture, to facilitate that earlier communication and set those realistic expectations. But that's also something that we thought about when looking at the implementations. There's so many steps and so many aspects of making a prognostication that's so difficult to bridge in that way. And I do think it's interesting that you mentioned that there's also cultural differences between different countries, and I would say the Netherlands is pretty progressive when it comes to stuff like that. But it's difficult to find kind of a balance in that. And so when we're looking at implementation and the work that we're doing here after, it's very difficult to determine how you would actually use this and how such algorithms can work in concurrence with the actual clinical practice that is happening. So I guess that's a long way of saying that it's very difficult, and you have to take such a multimodal approach. But the idea, I think, really of having such early prognostication, early tools is really to set those realistic expectations, to manage all other aspects of clinical care, if that makes sense to you.
Yep. No, fair enough. I'll let you get back to answering the other questions that have come in. Yeah.
Yes.
Very good.
So we have another question. So first, what about the prognostication of good outcome? That's a good question. So in this study, we only looked at poor outcome, but within the department, we are now branching to predict good outcome, or look at ways of predicting a good outcome as well. But as of now, this study was only limited to poor outcome, because that seems to be a very, very important outcome to be able to identify very quickly and early as well. And then the same question about external validation. So as I said before, we didn't do external validation in this study. We have tried some external validation after the conclusion of the study. So we used some public EEG challenge data and found results that are relatively comparable, but very interesting. We found that the quality of the EEG signal is very important, and that can really make a big difference in the prediction of a model like this. And lastly, the question about how did we handle the artifacts. So by using that custom-made algorithm to select those 5 minutes, we tried to minimize the number of artifacts within the epoch that was used. So hopefully the least number of artifacts, or close to none, were included in the model and the training of the model. But it's true that eventually it's very important to be able to handle different types of artifacts over time for potential real-time ICU bedside prediction. And I see another last question, I think. So the question reads, you processed each channel separately using a CNN. Did you also consider combining the channels at each time point to capture interactions between them? So the different channels were, if we go back to the picture of the shallow CNN by Schurmeister, the channel was indeed, it acted as a separate dimension. So the spatial filter that we used, and that's something that was inherent to the model that we used, compressed all the information from the different channels in a combined feature map. So in that way, the resulting feature map was a combination of the channels at each time point over time, if that makes sense. So even though the raw input was separate EEG channels within the CNN itself, kind of the spatial information that between each channel was compressed into and combined into a single dimension. So that was the approach that we used at this time, and I hope that answers the question. I see.
Well, looks like there's one more, and then I'll have a final one, and then we'll. This is very good. Thank you.
There's a lot of questions. We're happy.
Yeah, it's good.
People understood and are intrigued.
Yeah.
So the last question here from the audience is, a great advantage of CNN is explainability, which is highly important in clinical decision-making and trust in models, definitely. It'd be interesting to see if the model picks up on known patterns on something else. And I 100% agree with this, and I think it'd be very interesting to take this further and then kind of take this black box of the CNN that's happening and see if maybe it focused on particular patterns or parts of patterns, or what exactly picked up on in general. But I think to circle it back to the implementation, I think it's also very important when you're presenting with clinicians with such models. I think it's very important to have a certain level of explainability, and 100% agree that we should look forward to this, or research more into it, and future research to see how much they can find out about the inner workings of a CMM. But yes, that's a very good point.
All right, so I have one final question. And
Go for it.
We've been working a lot with spreading depolarizations, and I think they're a great predictor of poor outcome in patients with a brain injury. And I'm just wondering if well, first of all, have you ever thought about looking at those rather than just the EEG and the traditional bandwidth that we can see? Are you familiar with those at all?
If you could repeat what exactly?
With the spreading depolarizations.
No, I don't. I'm not very well versed in those.
Okay, well, we don't. We can talk later on that. But I just wonder if maybe your poor predictions might be picking up some scalp EEG representation of what you would normally see with an ECOG with a cortical electrode. So just to
right.
we can talk about it later.
Yeah. No, but it brings up a lot of questions and a lot of possibilities, and it's very exciting to see how this works if we could ever get to that. But very good thing to be looking at.
Well, this has been wonderful. Thank you so much. Say hi to Amsterdam for me.
I will. Thank you so much for having me.
And enjoy your Friday night. And thank you for all. We got a lot of folks from Europe in on this. And thank you for tuning in on your Friday night. Now go out and have a beer, have a drink.
I will. Thank you so much. Thank you. And thanks for the audience members. And if anyone has any questions, wants to further discuss, I'm always open to it. So find me somehow.
Well, thank you again. Thank you so much. And we'll be in touch.
Yes.
Thanks.
Bye.